Mm, properly. Mm, record yet? Okay. Mm. Okay. Anyone knows how to hide this one properly? Uh,
Is it, why don't you try hide with floating BD controls? Thing. Go to more. It said hide floating BD, could that be it?
where? High floating meeting control. Okay, right. Thank you so much. Okay, so okay, I will walk you guys through about like several topics or problems, and first one is like knapsacks and uh and we'll walk you guys through about problem reviews. So probably like Regularly also mentioned a knapsack problem on the class, right? Say so about the knapsack. The basic idea is simple. Like you have a set of items and which the corresponding values and weights, right? So your goal is to how to collect those items optimally by based on the value and the total of the weight must satisfy the condition of the bag that you bring in. Yeah. So here. Okay, so suppose you have a knapsack of capacity of W, you have a bag of weight of W, and you have n objects, and with the weight of from W1 to Wn, and the corresponding values of V1 to Vn, and your goal is to find the largest total of value of items. Like for example, like you have to choose the item that having the greatest total value, and it has to put right fit into the bag with the weight of with the capacity of W. So here, anyone guess about the state's action, goal test, and the path cost for this particular problem?
Could you suspend the previous slide just a little bit?
Sorry,
Could you suspend the previous slide just a little bit?
sorry. What did
Could
you?
you please switch to the previous slide?
Okay. Yeah.
Um, so I think state would be like just the subset itself. What's in this subset stuff?
And about the action, like put in and put out, like object being selected or not, right? And about the goal test, like is there any specific goals? Like because currently like we try to put the items in the bag like optimally. So we're not having any specific goal because it depends on the constraint that being listed on the problem. So here and about the state of evaluation function, meaning that the total value of the stuff being put it into the bag with satisfy the total weight, the total capacity of the bag. So here, formally, the knapsack problem is we have a set of items and each item has a weight and a value. So we also have the maximum of weight capacity for the knapsack. So our goal is to optimally choose the subset of item. Remember the subset of item so that the total of weight must satisfy the capacity of the bags and as well as try to maximize the total of value. So here, xi meaning that it is a one-hot encoding vectors of the items. With for example, you have n items, so the shape of that particular vector it is n. Okay. So so do you guys have any like guess about the size of the search space and as well as depth of search space, number of successors? It's a number of items. The size of the search space, like how many like states it would be. Yeah. Yeah. It's exponential. Sorry.
Exponential. With x being the amount of like total items available, there's no limit to the knapsack. For the first time you put x amount of items, and it's x minus 1.
So for each item, there are like two options, like we choose and we not choose. So if we have n items, so how many like how the state the state space would be 2 to the power of n, right? Yeah, 2 to the power of n. So basically, you can for each of the item you can choose or not choose that particular item to put into the backpack. And about the depth of search space, because this is a vector of n elements, so like you have to assign each of the items to be like choose or not choose, and essentially there are no terminals. Like the number of terminal nodes, it is like because we based on the assumption that all of the items must be satisfied by the total of the capacity and as well as try to maximize the total value. So there's no terminal nodes. And about the optimal value, so the optimal value would be the greatest values, the greatest total values that the items have to be put in. Yeah. Okay, so to solve the knapsacks, it is like a very difficult problem. So the NP complete meaning that there's no polynomial time algorithm that solves the problem like efficiently. And if we found one, it would be like it would solve on the NP problem. So about the okay, so we get some of the examples. So for example, like we have a set of books right here with the corresponding weight and a value, and we try to put these particular books and into the backpack of 15 kilogram, and we try to maximize the value we put in. So for example, like there are several algorithms that can tackle knapsack. So first one is dynamic programming. So this is like the algorithm that can provide an exact solution to this particular knapsack problem. And second one is uninformed search, meaning that you can use some several algorithm like VFS or DFS to tackle for the problem. Like we just blindly search for the state space. So the complexity would be like 2 to the power of n. And third one is like uninformed search, meaning that it is like a uniform cost search. for a star problem. So if we design a good heuristic, meaning that for example, like if we choose a subset of items, or if it exceeds the total of capacity, we would not going forward, but we try to branch and bound. We do some branch bound, meaning that we try to cut those branch out and try to move another different way. And the first one is like use like local search. Like you can use several algorithms like stimulate and annealing. So for it is not guaranteed for the optimal solution, but it is the good algorithm to provide a good solution. So let's examine like several algorithms that we might want to consider. So first one is greedy algorithm. So a most naive way to solve this problem is like, for example, you have a set of items, you want to see a set of items, and you want to choose the item ranking from their value, right? Like you want to choose the most valuable item in order to satisfy the capacity. So here, so for example, like your current state of the backpack would be 0 kilogram with a total value of $0, and the capacity still remains at 15 kilogram. So here you've got a set of items right here, and you try to sort them by value. Like you try to sort them by value, and you try to pick the items that having the greatest value. So here we can use like we can design some function like determine the value density for a particular object. So for example, in this the first one, we have got a weight and the value. We can measure the value density, meaning 2.5, meaning that if we put this item to the bag, so how would likely it would fill the bag, and we can obtain the valuable value. Yeah. So for example, here we try to greedily pack the items sequentially. So for this one, we pack the current backpack. Well, if we try to pack this one, the total capacity would reduce to 11 kilogram, and the total value it would increase by $10. And we choose the next, we choose gray book, and the remaining capacity would decrease to 9 kilogram, and eventually until it fill out the backpack. So here, if we try to pack the green book, it would exceed the total of capacity, and here we only obtain a knapsack of having the total value of only $15. But there are more optimal way to pack a backpack, but this is only a 3D solution. So there are other approach like dynamic programming, which we could consider for. So for example, in this one, the key idea is the key ideas on this problem is it depends on two properties, like how many items are we considering. So for example, we have n items, and we consider like the first half of the items, and if we consider one more items, how would the state would transition, and the total of the weight of the bag is holding. So for example, if we hold n items and the total weight of the bag is holding, like for example, like 10 kilogram, if we try to grab more items into the set that we are holding, so how would it change the total weight of the bag? So we try to design a target function, meaning that our target function is the total value of the items in the bag right here. So we try to maximize this particular function, but have to strictly follow the rules of not exceeding the bag's capacity. So for each item, we have two options, like select that item and not selecting that item. So here, the total value of the items in the bag, it is maximum by between the putting the n-1 items into the bag, having the weight W, and the value of putting n item together with putting n-1 items into the bag, having the weight of the minus the current weight of the current item that we are considering. So essentially that for each item we consider we have two options. If we try to put that item into our bag, so meaning that the capacity of the bag would decrease and the total value would increase, but we try to follow the strict rules. And if we try not selecting that items, it would be different. So we would disregard that item and we move forward. So here we design a target function for our dynamic programming algorithm, meaning that we call L, meaning that the maximal, like the max value of the items in the bag when we consider the first I items, and the weight of the bag must not exceed W. So this is a common way when you guys are dealing with dynamic programming and stuff. We have to consider the first item with respect to a condition. So if you try to inject more condition, the target function would be different. It would increase sequentially if you try to condition more. So the size of the target function would change and would increase correspondingly. So in this case, if we try to modulate our function like this, we have the target function for if we consider the first 0 item with the corresponding weight, it would be always 0, right? So this is a anchoring space state of the dynamic programming. So here we try to formulate it. So if there are two options, right? So if we are considering the first item and we choose that particular item and put it into our bag, so the cost function would be different. So if we try to choose the item, so we have to take the target function when we're considering the I-1 items, minus to the weight of that current item and plus the value, because we try to put that item into our bag. So we have to check whether or not the capacity of the bag is able to put this particular item into, and we plus the current value. So if we try not choosing the item, the target function would be like based on the N-1 items that we're considering. So the total cost function would be like this. You guys have any questions regarding the setting up the target function for dynamic programming? So this is a common way. This is the most common way. If you try to deal with other dynamic programming, it would be follow the same. So because we have to select or not select the item, so we have to formulate it in the sequential manner like this, like starting from like 1 to like, for example, like considering first 2, considering first 3, and considering first 4. It is not backward. It is like a one-dimensional forward only, because it is dynamic programming. So the state that you try to modulate later on would not affect the previous one. It follows the strict rules of dynamic programming. Yeah. So I'll walk you guys through the example like this. So if we have the capacity, the bag capacity of 13, and we have 5 items, and each of the items having the weight and the corresponding weight and the value. So here we try to formulate it in this way. So here, this is our target function, and this is our like a function right here, and we try to fill it out. So for example, like for the bag size of this is for the bag size, W is for the bag size, and this is for the item. So if you consider first 0 items for the bag size of 1 kilogram, the total value would be 0, because you are not considering anything, because our items, it is indexing from 1 to 5. So if you're considering like first 0 items, it would be like the total value would be 0 only, and it would sequential like this. And so if you try to consider the first item with the capacity of your bag is equal to 0, it would be 0, right? And you move forward until until if you considering the first one items here, this is the first one items, but the back with the capacity capacity of 3, it would be like 4 because it would consider the putting the first item into the bag having the capacity of 3. Yeah, this is the optimal way to do so. You move forward. So if you consider the first one item and with a bag of having the capacity of 4, it would be 4 also. Move forward. Because we are considering only the first one items only, but the capacity increase, it doesn't mean like if the capacity increase, but the state must be remain unchanged because we are only considering the first item only. Yeah. Right here. So if we try to move to the second items, so what would be the change right here? So if we're considering the first 2 items, with the capacity, with a bag capacity of 3, so it would take the previous result right here 4 down here, meaning that you are considering the 2 items, but you only put the first item into the bag having the capacity of 3. So it would satisfy the condition. Here, things to change differently. So if you're considering, a bag of the bag with the maximum capacity of 4, and you're considering the first 2 items, and if you try to put the first item into our bag with the capacity of 4, the total value is only 4 only. But if you try to put the item having the if you try to put the second item with the weight of 4, satisfying the bag capacity and having the greatest value, so the value would change right here. You can see. And here you try to iterate over the matrix and try to formulate and try to following this particular function, the total value of having. So for example, right here, if you're considering the first 5 items and the bag capacity of having like the capacity weight of 12 kilogram, so the total value you would get would be 15. But if you try to considering the bag total capacity of 13, it would change differently because it would depends on the state that you iterate over previously, and it would not affect the previous state. The current state would not affect the previous state. It is the rules and for dynamic programming. Yeah. So essentially, for example, in this particular case, if you have 5 items with this particular weight and corresponding values, and having the total capacity of your bag is 13 kilogram, so the total value that you would get would be 16. Yeah, and you could seamlessly trace it back. So for example, in this case, you could trace it back. So for example, in this case, you have about like $16 having the capacity weight of 13. You could essentially trace it back to choose to see how's the item being selected. So here you can see that when considering the 5 items and considering the 4 items, you can see the transition from the 4th row to the 5th row right here, meaning that the model like the algorithm tends to choose that last item, so it would take the last item. Yeah, it would take the last item, and you iterate from the 5th row to the 0th row in order to see how many to see the set of items being selected. Okay. Do you guys have any questions about the algorithm? This is a most basic dynamic programming, not the most basic, but the most common dynamic programming problems, and everybody tends to know this particular problem. Okay, so if you guys like having any like problem that needing to solve with dynamic programming, just follow the formulation of Knapsack. Every dynamic programming follow the same problem of Knapsacks. Not every problems, but the problem based on the Knapsacks, yeah, tends to follow this particular formulation. So here we try to work through some of the other way to tackle the knapsack problem, one of which is genetic algorithm. Do you guys familiar with the genetic algorithm? So essentially you have a data right here. The data is the data that provided by the problem right here, and you tend to initialize your population. First of all, the first step into like in order to solve a genetic algorithm problem is to initialize your population, meaning that you have to formulate how to represent the how to represent the chromosomes. So for example, in this case, because the state right here, it is choose or not choose. So you can seamlessly use one hot encoding vectors like this, 1 0 1 1 0, meaning that if it toggles to 1, meaning that you choose that item. But if it toggles to 0, it means that you would not choose that items. And you have to design the fitness function. So for example, in this case, if this is the vectors that being inputted into like, so if it is the state, you have to calculate how fit is the state. So for example, if you have to calculate how many like the total value of this state, and you have to calculate how much weight it takes. So if it exceeds the total of the bag capacity, it would be, the fitness would be 0. But if it still fits the condition that being set out, so the total value, the fitness, it would be the same as the total value. Yeah. So for example, in this one, okay. So for example, in this one, we start by initializing our chromosomes. So for example, in this case, for the first chromosome, it is one state, and second state, and third state, and fourth state. So the first one meaning that you choose the green book and the yellow book, and the second one meaning that you choose the gray book and the pink book, and for the third one, it's meaning that you choose green and gray. So this is basically the same. So here, so for example, this one, you have to calculate the fitness of for each of the chromosome. So for example, in this case, it exceeds the total capacity. So it would be like 0. So but in this one, it fits the total capacity, but it exceeds, but it is lower than the other two. So for example, this one, when we took the green and the gray book, if the total value, it would be 6. And you try to choose top K chromosome that being fitted into the bag. So here, when you choose 2, you just set those 2 parents and you do some crossover. So there are multiple ways. To do so. Yeah, you simply just can use like some simple basic very simple basic crossover operation, or you can use like Boolean operation for manipulating the bits, and you know finally you obtain a set of offspring, and here you put those offspring back into your population, and you put that offspring back into your population, and if and you can randomly choose one of the offspring to do some mutation, meaning that you just flip one of the bits in order to increase the diversity of your population. And here you just repeat the step in order to obtain the final results. Yeah. So here, so besides Knapsack, there are several problems that can be solved by dynamic programming, genetic algorithm, or greedy algorithm, meaning that coin sum. So for example, for coin sum, the problem state that if you have a set of coin and it would ask you like how can I select a subset of coin that can form a like a total value of, for example, like $15. So how can I select this subset of coins so that I can obtain any like certain type of value? And about coin change, so for example, if I have so for example, for coin change, if I have a set of coin and I want to exchange for other, and I want to exchange them, for example, like $15. I want to exchange $15 using this set of coin. So there could be like how many like I want to exchange a least number of coin in order to like give away, like for example, like $15, but using the minimum, like the least number of coin possible. And could be like time scheduling, meaning that if you have like certain type of jobs having like a time stamps, and you want to organize them in order to maximize your profit, this could be also solved by genetic algorithm, dynamic programming, and 3D stuff. And longest common subsequence, meaning that, for example, you have two strings and you want to calculate the not the semantically, but you want to calculate how different it is. This could be solved by longest common subsequence. Okay, so do you guys have any questions about like knapsacks and problem formulation and solution? So if not, I will go through the reviews. So do you guys have any like so the first question is like explain why problem formulation must follow the goal formulation. Do you guys have any ideas? Like could be based on the knapsacks that we just saw earlier. Yeah. Okay. So about the problem formulation is that the reason is very simple. Like the goal tell us what we're trying to achieve. And once we know that, we can structure the problem correctly. So for example, back to the knapsack problem earlier, that we want to select the items that try to maximize the value, but following the constraint, meaning that the total of weight must satisfy the bag. So that you have to formulate the state space and how the transition and how can we achieve our goal. Yeah. So let's look at this particular example. So for example, like there are 6 glasses in a row and each with a lock. So each of the first 5 boxes holds a key unlocking for the next box in the line. So the next box hold the banana. So you have a key to for the first box and you want to obtain the banana. So what's our goal? To have a banana, right? Sorry? Yeah, that's right. So the goal state is that like you want to obtain a banana, and the successor function is that you open any box you have a key for and get the content next for opening the box. Yeah. And the cost function would be the number of action. Yeah. So if you try to if in the future, if you have any like problem, if you break it into like how we solve the problem, like you have to break it down, like how to obtain the goal state and what's your goal and what's your transition state and what's your total like cost function, you can solve any problem with it. Okay. So for example, in this one, you start with a sequence like this, and in a general way, in like any sequence made of A, B, C, E, and you can transform this sequence using the following inequalities, meaning that the condition. So right here, there's a equalities, and for example, like for A, B, B, C, you can transform it into A, E, C following the condition right here. And then AC, you can transform to E. So what's your goal? So your goal is to produce a sequence E. So what's your goal? Your goal is also like transforming into the sequence E, right? And successful function is meaning that you apply that equalities into your like your current string to apply for the next iteration, and the cost function would be a number of transformation. So this could be like solved by dynamic programming or like greedy algorithm, but it is like a NP hard. So for example, in this one exercise right here, so consider the problem of finding the shortest path between 2 points on the plane. So for example, in this one is like when you transition from every like from each of the destination right here, it is not like a fixed integers, but it is on a float base, and your goal is to from S you can transform to G, but you try to avoid this obstacle. Yeah. So how many states are there and how many paths are there to the goal? Considering this is a float grid, you guys have any like do you have do you guys have any ideas of like how many states are there when this is the problem that you're trying to solve? Yeah. And how many paths are there to the goal? So because this is the floating grid, so the total of states, it would be like infinite. And how many paths are there? So it would be infinite, right? So for example, considering this room, so how many way you can walk from this to like where you can walk outside of this particular room? Infinite, right? You can walk anywhere. So it's basically like the problem formulation and how can we discretize things to make things more easier. So for example, in this particular case, if you try to discretize this grid into like integer, like integer based grid, it would be more easier. Like for example, like you try to partition this room into multiple blocks, and you try to move from this particular location outside of this room, you can seamlessly calculate how many ways you can do so, and and calculate what's the shortest way to do so. Yeah. And you guys have any idea about like explaining why the shortest path from one polygon vertex to any other in the scene must consist of the straight line segment joining for the purchase of polygon? I believe this is like based on the geometry, right? Like is the straight line would be the shortest one. Yeah. Okay, so proof of the following thing, like breadth first search. I believe Professor Rackley have also covered about these topics, right? Like breadth first search is a special case of uniform cost search. You guys have any like idea, like why is it? So yeah.
I was gonna say practice is uniform on search if the costs are always one. That's the same thing as first search.
Yeah, that's right. Yeah. That's right. Yeah, preference search when you try to formulate it in a way that, for example, if you try to work and each step it takes about like a unit of value, so it would be just similar like a preference search, uniform cost search. So okay. You guys have any guess about like what's like depth first search is a special case of best first tree search? You guys have any idea like why depth first search is a special case of best first tree search? Okay, so depth first search, it can be seen as a special case of best first tree search by choosing the right scoring function. So, for example, like for the depth first search, the idea is that you try to reach to the lowest, meaning that, for example, you have a root of a tree and you try to reach to the lowest like you try to reach to the lowest state and you try to move it backwards. So here you can formulate it in the right way. So if we define the best first score so that the deeper the node is, so that deeper the node looks better, and then the best first search which exactly the same as the best first tree search right here. And if you try to formulate it in a way of, for example, you have a tree of state right here, and you try to formulate it for each of the height of the tree, it would be equal to the negative of the depth of the tree. Okay. And uniform cost search is a special case of A-star search. So essentially, that if you try to do A-star search with H and equal to 0, it would be the same as uniform cost search. Okay. So I'll try to revisit traveling salesperson, right? So for example, given a graph right here, and you try and having multiple edge, so your task is to find a closed tour, meaning that the cycle of the minimum length visiting all the cities. And there are a lot of applications down for this particular problem, and it could be also solved by genetic algorithm and several searching algorithm. Yeah, so for example, in this one, there are about more than 13,000 cities in the US, and for example, if you try to place them in the sequence, meaning that, for example, you visiting the first city and move on to the second city and third city, it would be many ways, a lot of the total possible way, it is very large, and then state space would be very large. So is there any optimal way to do so? Meaning that, so this is one of the figure in the research that the people the people provided the optimal tour of visiting the US by moving through the cities. Yeah. So here, have anyone know about have you guys heard about Hamiltonian path? Hamiltonian path. Have you guys heard about it? Yeah. Okay. So Hamiltonian path it is a cycle Hamiltonian cycle is we try to visit every node once and return, and TSB is finding the shortest Hamiltonian cycle, meaning that the traveling salesman person problem is more stricter than Hamiltonian path, meaning that, for example, you're given a graph and you try to ask the model to whether or not it could form a such cycle, and the traveling salesperson problem is that given the graph and you can form that cycle, and you have to calculate for the minimum possible way where we can walk through every city and return with the least total of the cost. So here, I believe last week Anna has also walked you guys through about TSB, right? How to, when we transition from state to state, where we can calculate the cost of G and calculate the cost of H by using minimum spanning tree, right? I believe so, right? So you guys have any questions about this particular problem, traveling salesperson stuff? And do you guys know why minimum spanning tree, it is a way where we can calculate the heuristic? You guys have any idea? So for example, if you try to work, for example, in this, so let's look at this particular example. If you try to work from this city to this city and to this city to this city, this is cities that you have been visited. So here, this is the set of cities that you have not visited. So let's assume that this city is connected. So here, if you try to construct the minimum spanning tree, it would try to span these cities with edges, but it is not guaranteed that it would try to. But it is not guaranteed that this minimum spanning tree plus the path that you just visited would form the cycle. So here, in this case, so for example, in this case, for this set of the cities, right here and you try to calculate the minimum spanning tree, it is just only the heuristic of this set of cities, meaning that the total of the edge that needed to connect this city, it is like the value of the total of the edge of used to connecting these cities. So it is not guaranteed to form a cycle backward into the path that you just visited. It's just only the estimate or the heuristic of that particular problem. Yeah. So I believe this is the important observation, and it might crucial for the part of your exams. So if you guys have any questions related, you can freely ask. So that's it. This is the proof for why minimum spanning tree is like stricter than traveling salesperson. Minimum spanning tree meaning that it only calculate the cost in order to connect the cities, but it is not guaranteed to obtain the cycle backward. You backward with the path that you just visit in the traveling salesperson path. Yeah. Okay, so that's it. You guys have any questions, and you guys need me to walk you guys through in order to the preparation for the exams? Okay. Okay, I believe so.